We're back with Gruber Motor Company, where in this episode we dig deep into the Tesla Roadster. This is going to be a rather long, in-depth look at the first generation Roadster, walking through its many odd features, maintenance items, and component-level technical education from both Pete Gruber Sr. and Jr. If you haven't yet, check out our first video in our Gruber Motor Company series, where we go through what their company does to keep alive EVs that are no longer supported by the factory. Make sure to subscribe for more on Gruber, as well as our other EV content from track tests to road trips. Now let's get into the weird and wonderful world of the Generation 1 Roadster.
We are at the interior of a 1.5 Roadster. Again, the 1.5 Roadster is the early model Roadster. They were originally 1.0s. However, the reason why they were changed from 1.0 to 1.5 is they had an issue with their two-speed transmissions. They changed them to single-speed transmissions, and because they had the transmission, they decided they were going to add a stick shift. Nowadays, it doesn't have any other function other than moving you from neutral into drive or into reverse. But it's still an interesting feature. Moving on to the 2.0 and 2.5 Roadsters, because we only have reverse drive, they added a button system. So you can see there's quite a difference between the two in that regard. When they first built this car, there weren't really any electric vehicles on the road at the time, so they were kind of coming up with how to design and build an electric car, and one of the first things they decided was, why do we need a 12-volt battery? So with the first generation Roadsters, they did not have a 12-volt battery. The way they got their 12-volt power was from a DC to DC converter that was inside of the main battery pack. Now there are two DC to DC converters inside of this Roadster. There is a smaller one, which is your 12-volt battery equivalent, and there's a second one which powers the rest of the 12-volt systems when the main battery is alive and powering everything. However, the reason for a 12-volt battery in an electric vehicle is when the high voltage system has a problem, you have to cut power. If there's high voltage present, the last thing you want to do is get anywhere near the car and expose yourself to it. So what they do is they shut down the high voltage circuit, and the 12-volt power is meant to keep on important things like your hazard lights. It keeps your instruments alive, and that's the reason why you have a 12-volt battery in your car. With the original Roadsters, again, let's go to a battery and let's see what that 12-volt DC to DC converter looks like. So we're at a 1.5 battery right now. Your first two sheets, starting from 1 counting up to 11, you have a E-connect here in between the sheets. This E-connect has a wire tapped into it that you will not find on a 2.0 battery, because these two sheets have a DC to DC converter right here that's going to convert the power coming out of these to create your 12 volts for your car. And this is your battery backup system right here. If there's ever an issue and the high voltage system has to shut down, this little guy is going to take over as your 12-volt battery. One of the issues, however, is because this is your 12-volt battery, if for some reason the battery decides to shut off the high voltage system for any reason, either during normal operation or during a problem, these two sheets are going to drain. If they're not draining at the same rate as the rest of these sheets, you're going to create an imbalance in the battery. And that's a typical issue with the 1.5 Roadsters. These two sheets get imbalanced from the rest of the batteries, and what the fix was in the past was to replace these or to simply recharge them.
This is the drive portion of a Tesla Roadster vehicle. This is what converts all of the DC in the battery system to three-phase AC to power a three-phase AC induction motor, which was what was invented by Nikolai Tesla over 100 years ago. Inside this box, you can see a bunch of electronics. There are three phases, or three inverter stacks, and there's some logic here that actually controls all of this. The DC comes into these two fuses here, and then gets converted to three-phase AC, which comes out this port here and goes down to the three-phase AC induction motor, which then couples to a transaxle and converts all of that kinetic energy to the wheels. What we're doing with these PEMs is both repairs and upgrades. This, being an electronic module, has components in it that will actually deteriorate with age. These are electrolytic capacitors here. They're used as filters in the output of the inverter to help create a clean sine wave. And as they age, they become resistive, and they eventually begin to put a heavy load on the inverters. In advanced cases, these capacitors are actually known to explode. And I have a sample of one here that came out of a UPS. And you can see this one blew its top. When the shrapnel blows, this is conductive material, so you're blowing metal fragments all throughout this logic. We had one in Germany that actually blew its top. There was debris all throughout the PEM, and luckily nothing shorted. We had to vacuum, blow it out, and the PEM began to work again. This is a replacement item for Tesla. They charge about $10,000 for one of these PEMs, so you see how important it is to actually take good care of this. Here you can see the inverter boards. These do not have the upgraded capacitors yet, and this is called the Megapole logic board. And on the back side of this are transistors. And instead of going with one large form factor transistor per phase like we do in the UPS world, Tesla decided to go with multiple transistors per phase. Now, some of the things that we do besides changing capacitors on these boards is we replace it's called insulating material, which is the thermal barrier between the transistors and these aluminum heat sinks. You can't really see them here because we don't have one apart. The original design used a material that deteriorates with age, and no one really knew that at the time these things were being created. Years later, as we started to take these apart and repair them, we found crumbling, deteriorating insulating material. And what happens in the advanced cases is the transistor will short against ground and blow a transistor and an inverter stack to boot. So we change all the insulating material with a more resilient, robust material. We change all of the contactors. There are relays, contactors. Those are wear items. They get pitted and they deteriorate with age. There's a small 12-volt DC fan in here, like in your PC. And of course that has a bearing in it, so that deteriorates. And then we do engineering change orders. There's some design flaws that did not manifest themselves until later on. And part of that is these connectors underneath the PEM here. We actually retrofit them so they don't burn out.
On the Roadster touchscreen, there's a difference between the 1.5 and 2.0. I mean, other than their placement, they're pretty much the same, other than in the 2.0 and 2.5. If you go to your information screen here, on the second page, you'll find a memorial button. This memorializes 3 Tesla Roadster engineers that died in a plane crash in 2010. If you were to tap in an area where there isn't any button or interaction or interactionable area, what you'll do is you'll tap repeatedly like this, and a service diagnostic screen will come up. Punch in the code 1050, which is 1050 Bing Street, one of their original addresses for Tesla, and that will get you access to your diagnostic menu. Inside of the diagnostic menu, you'll have access to a whole slew of information and functions. I don't recommend playing with a lot of the functions. However, if you were to jump into, say, this vitals menu, this is a fun one to watch while you're driving the car. It gives you an idea of where your temperatures are at, your minimum brick voltage is. So it's nice when you're driving to see if you're getting a power limiting issue. Perhaps what you're looking at is your PEM is getting too hot. If your PEM is getting hot, that would probably lead you into a need to get your PEM annual done, because you've got leaves or debris that's caking on underneath the PEM, basically creating a blanket and just keeping the heat in rather than letting the air do what the air does, is pick up the heat and pull it away from the PEM. So these are fun screens to look at when we're diagnosing the cars. I've got all the information I need here about the battery, sans most of the other bricks that I may want to look at voltages for, but I can see battery voltages for the 12-volt battery. I can see the entire battery voltage here. You'll probably see this current here change when you're driving the car. You'll see current draw from the battery. What else do we have in here? There's recent alerts. So this will show you all of the recent alerts that have occurred on the car. The other place you can get all of this information is from your log file. And again, your log file is downloaded from your USB port down here underneath the center console. It's in the same place on both of the Roadsters, the 1.5s and the 2Xs. In controls, if you were to change your 12-volt battery, you can turn off the 12-volt system by inhibiting the APS here. And then if you ever have a problem, if you haven't taken the Roadster in for service and you're getting the reminder, take it in for service. That's usually to tell you that it's been a year, it's time to get your annual done. However, if you've done the annual yourself, or you know that you don't need service and it wasn't reset, your reset is here. Reset service interval will get rid of your maintenance warning. And if we back out, this is one that I use quite often when I receive vehicles in. This alert text here, unlike the Model S's, we can actually change the alert text to say something other than there's an issue, take the car to Tesla. This will tell us exactly what's going on with the car to some degree of accuracy. It'll at least tell you which system's having the problem, and it will give you an idea of what the problem is. And that will definitely help in determining what sort of an issue you're dealing with, as opposed to contact Tesla, there's a problem. So changing your alert text here from end user to debug will give you far more descriptive alerts. Moving on to the HVAC system with the cars. Arizona drivers will probably know better than most. Summer is not a great time to drive these. One of the issues that occurs during the summers out here is you're driving the car, you've got the AC on, obviously, because it's way too hot out. However, once you've driven the car for a little while, it'll vary from car to car depending on all sorts of various factors. But once you've reached a thermal limit and the battery's decided that it needs the AC cooling itself, you have a Model S or X or 3, what'll happen is normally in those, you'll share the AC system. There's a split separate loop. However, in the Roadster, there's only one AC loop. If the battery needs the AC refrigerant more than you do, you lose your AC cooling in the car and the battery gets cooling. So you'll be driving in 115-degree weather, and the next thing you know, your AC's out, you're sweating, and there's no way to turn it back on because the battery's decided, I'm hotter than you, and too bad. You can put your hard top on, you can put your soft top on, take it off, put it on if the weather changes. But the cooling system in these isn't nearly as great as the Model S's. They do have a problem with overheating, so they're not great for tracking. But for zipping around town, they're perfect. The mileage on them right now, you're not going to find too many Roadsters that are still sitting over 200 miles unless they have a 3.0 pack. If you find one with a 2.0 sitting over 200, grab it. That's a very good thing. There aren't any that are sitting like that, so if you do find one, that's a really excellent thing to see. But typically you'll find the cars sitting anywhere from 175 miles to, on the low end, about 150, 140 miles. And there's those that are 130 or less, but those ones will likely be over 100,000 miles. They're well-driven cars. But again, they're like any other electric vehicle or any other Tesla for that matter. Maintenance on them is really not much. The Roadsters, on the other hand, there's a little extra you need to do. Again, you're not going to be changing fluids that often. You're not going to be changing brake pads. But one thing that you will need to do at least every year on them is you will need to pull the PEM. Pulling the PEM requires removing, and I should probably note, PEM is short for Power Electronics Module. That is this box here. This one we just installed, we're putting back in. But what we've done is we've removed this Power Electronics Module here. We've put it onto a table, and when you flip it to the underside, there are cooling openings on the bottom. There's a fan underneath that's going to blow air up underneath the PEM and across the 3 boards that you had seen earlier in the video. Those are your 3 inverter boards for your 3 phases going down to the motor. The reason you have to clean this every year is because the fans are sitting down below at the bottom of the car. There's a lot of dust and dirt down there. So all the cool air that it's supposed to be pulling in, it's also pulling in leaves, it's pulling in dirt, hair, dust, everything gets sucked up into the fans and sent straight up underneath the PEM, where it accumulates and creates this sort of blanket. When that happens, well, the temperatures will get higher and you'll likely have power limiting problems, or you'll find that the fans are running more often. When the fans run more often, it's sort of a negative feedback loop. Your fan connector burns out in that scenario sometimes. Most of the times they do survive, but one of the problems that we find with those connectors is just upon reinsertion, the connector on the inside of the PEM will get pushed back. And what you have happening now is less contact than a normally seated pin. So that unseated pin is going to cause more contact resistance, which eventually burns up the connector. So it's just always a good idea to keep the PEM clean underneath. And you're going to have to just keep an eye on your connectors. Our fix for it is backfilling the connector with epoxy. Make sure you're not putting anything in with steel shavings, steel reinforced. Any sort of a metal reinforcement is not going to be a good idea. It's going to short all the pins together. So make sure you're just using a standard epoxy. Because this will likely not be the car that you're driving across the country, like your Model S, your X, your 3, this will likely become the garage queen, as most call it. If it does end up sitting in the garage more often, they do tend to discharge a bit quicker than the other Model S's. You may forget about it, you may plug it in. Most of the brick battery issues we've seen in the past have to do with a Roadster left on the charger, and then owners go on vacation, they go on a road trip, they leave the car unattended. It's plugged into the wall, so everything should be fine. However, what tends to happen is on the yellow spare connectors, they have a GFCI built into them. That GFCI can trip, and if it trips, it requires a manual reset. And if no one is there to manually reset that, the car doesn't charge. However, back in the day, not nowadays, back in the day, Tesla had a program whereby they could see the battery drain, and they would get notifications about your battery getting to a low state of charge, getting dangerously low, and then they would email you or call you and say, listen, we see that your battery's getting low, you should probably go check on it, get it charging again. And that helped with most of the brick battery problems, because now you're not going to get a brick battery. Tesla was there to remind you that, hey, it's not charging. Nowadays, we've got OVMS, which helps. In fact, you can remotely start a charge if it does have a problem. However, again, if the GFCI trips, you can't remotely start the charge, but if you have a friend, family member that you can call, you can have them reset the GFCI, and that will fix the problem 9 times out of 10. Another good thing to do if the car isn't being used and you don't plan on using it, keep it in storage mode. One thing to note though, the range decline is normal. Don't freak out. What it's doing is it's going to keep the car in a lower state of charge. It's going to take it from your typical 80-85% where the car would normally be at a full charge and bring it down to 30. Lithium lasts longer in a lower state of charge. So it's better for this battery here to be sitting in a lower state of charge for a long period of time. However, if you wanted to drive the car, you're now going to have to charge the car back up, but you have the added benefit of the car being able to sit in storage mode, preserving the lithium cells and keeping them at a lower state of charge. Though, again, I'd hate to continue to warn you and give you caveats, but being at a lower state of charge also puts you at risk if there is ever a problem with your charger. The car will normally charge the battery as it needs to keep it at around 30%. However, you're also closer to 0%. So you definitely want to keep an eye on these cars. If you can get any sort of remote monitoring, or you can get someone to come and check on the car, I would say once a week, once every 2 weeks is typically enough. If you're in storage mode, I would probably push that to more like once a week. Because they will drop a bit quicker at a lower state of charge. But yeah, you definitely have to babysit the cars. However, if you don't want to deal with any of this at all, the absolute best thing that you can do is, if, like me, you've got thinner arms and you can reach, if you were to reach in back behind here, in this spot, there is a plug. And this plug is your battery disconnect. Pulling this out from the battery will disconnect the high voltage. That will preserve the battery. To give you some idea of preservation, we've had a fully charged battery sitting here in the Phoenix summer heat outside with that battery plug pulled. And by the end of the summer, when we plugged it back in, it lost 3 miles range. Here's your Roadster charger. This is your charge cable. It is a large, bulky, Amphenol mil-spec type connector. Very interesting, definitely different than what you're typically used to on other Teslas. And what we've got on the other end of this fat cable is one of the original Roadster high-power chargers. Your Model S has, or Model S, X, and 3 will have a high-power wall charger. This is the original charger. This one will only charge at 70 amps, however. That was the max that they put on the Roadsters at the time. In fact, there was a firmware issue with Roadsters that they changed in a somewhat recent update. If you had a CAN Senior, it would have an 80 amp pilot signal. The Roadster didn't know what that was. At the time, there was no 80 amp charger. This was the biggest charger that they had available, so they had to fix that in the firmware that when it sees an 80 amp signal, it would only charge to 70. So, but this is one of the original chargers here that we use with our Roadsters to charge them at 70. And this here is a cable that when the Model S first came out, a lot of the original Roadster owners bought a Model S, and they still had their high-power wall charger here, high-power charger. So what Tesla did was they took the charge cable. This is from a Roadster. This is what sits inside the charge port. And then this cable here would run over to the battery, to the PEM, and this would plug into the PEM so you could charge the car. So someone got the bright idea, hey, why don't we just put a Model S connector on the end, and then the Roadster owners that still have this charger that don't want to install the new one yet can use this cable to charge their Model S. So we use this to charge Model S's, 3s, and X's when they come in. This is a Tesla product. We did not build this. Tesla used a bunch of these charge inlet cables from the Roadster, and we hope they didn't deplete the supply too much.
This is one of 11 sheets of a battery pack in a Tesla Roadster. The total battery count in a Tesla Roadster is 6,831 lithium-ion cells, the same as the vape cigarette cells, 18650s. This sheet has 9 bricks, which are connected in parallel for a total voltage around 35 volts, and then they connect 11 of those in series to get up near 400 volts string voltage. Each of these cells has fusible links, and what we've been doing with this one is actually snipping out the highly resistive cells in this brick. We're still perfecting that process because currently Tesla is not making any Roadster battery packs, and our ability to find Roadster batteries from donor cars is been hit and miss in the industry. There aren't that many being totaled these days, and those that are being bought up by customers. We discovered a method for recovering battery packs, which included building our own power supplies. And here's an example of how we did this. Inside 480 volt UPSs, they have a 480 to 120 transformer to power all of the instrumentation in the UPS. So we simply inverted the transformer. We feed it with a variac, 0 to 130 volts on the 120 volt side, and then the 480 volt side goes through a rectifier, capacitor, filter, and we're able to create a 400 volt power supply variable. We started to use these to do a string charge across the battery pack on a bricked dead Roadster. By doing that string charge in a very controlled way, we were able to wake the car back up. At around 330, 350 volts or so, the car would come back to life. It would talk to us. It would start beeping. It would tell us that the charge is low, and we were then able to plug back into the main port here and allow the much more sophisticated Tesla battery management system to take over, balance the cells, and recharge the car. We've recovered a number of cars like this. In a more advanced case, if it doesn't respond to that type of recovery because it had been bricked longer than 3 to 6 months, we then have to pull the battery pack. And let me show you what that looks like. We decide which of these sheets are causing a problem, and it's usually a brick in a sheet or multiple bricks in a sheet that have been allowed to get below 2 volts. And there's a chemical reaction that occurs in these 18650 cells. If you drop below 2 volts, they actually begin to destroy themselves. So by the time we have this pack open, we then find the sheets that aren't coming back up, and we can actually charge one sheet at a time to see where it's going to end up and how it's going to hold. And in some cases, we have to change the sheets. In this particular pack, we've got 4 sheets that have been replaced. Anything with a white sticker on it has been a replacement sheet. Then we again charge and put it back together, and the car usually comes back to life at this point. Now, one thing to point out here is this pack takes about a day and a half to properly remove, open up, and to assess. If you notice inside this battery pack, there are fuses, there are contactors. This is the DC to DC converter. This is the part that takes 400 volts DC and charges the 12-volt battery, which then powers headlights and stereo system and some of the 12-volt devices in the car. Here's some more fuses, circuit board, some more fuses, contactors. The point here being is this car was not really designed to be serviced, easily at least. Had there been more time, what Tesla could have thought about was putting a hatch back here, because that portion of the battery is accessible back here, and putting all of the wear items underneath that hatch so it's more serviceable. We have an aftermarket product we're developing where we take this battery and actually place it in the trunk of the car inside a little case with a 12-volt meter on it, so the owner can always see the condition and state of the battery. And to replace it, I can show you here, is as simple as cracking open the case and unplugging a couple of fast-on tabs, and you've got a new battery. Here's an example of what we're going to be developing. There's a little meter there, and then inside is just simply a 1212 battery, which is actually better than the one that was in the car, and it will allow quick replacement. I have alligator clips here now because we have this meter connected to it, but it will eventually have a couple of fast-on tab cables. And as you can see, this is a Gruber battery. We also make batteries, and we put these in UPSs, and these are designed for electronic applications. And unlike the battery that's in the car, which is a 12-volt, 8-amp-hour battery, this is a 1212, and it's completely maintenance-free. The way these cars come to us is there's always a backstory when a car arrives here.
And this is where we're going to end part 2 of the Gruber Motor Company series here on the Out of Spec Motoring YouTube channel. Up next, we're going to go through the individual unique stories of each car that's arrived at Gruber for servicing. Some of them are really funny. We'll see you next time here on Out of Spec Motoring.